a phenomenon of interference and a way of exploring interference. So it's through the two-slit experiment, it's through the soap bubbles that we're going to see the interference, we're going to observe the interference of light. Just to give you a little context, I mentioned this before, so a famous argument in physics, if you went back a few hundred years, was between two famous scientists. One was an English scientist, one was a Dutch scientist, Newton and Huygens, and they argued on and on, like husband and wife, I guess. They argued on and on about whether light was waves or particles. And they never resolved that argument about light being waves or particles. Reflection and refraction can be described, understood, as light being either a wave or a particle. So reflection and refraction can't distinguish between light being a wave or a particle. You can explain refraction, for example, by the slowing down of light waves in a higher refractive material, or the slowing down of light particles in a higher refractive index material. So refraction can't distinguish light from being a particle, being a wave. The effects that we're going to look at in this class, next class, interference, diffraction, are wave-like properties, are wave-like characteristics. They are not particle-like properties. They are not particle-like characteristics. So they do show that waves exhibit, light exhibits wave-like properties. So that's the context. Okay. So interference occurs when two waves meet one another or collide with one another. So let's just take a moment and imagine the collision of two waves with one another and compare it in our minds with the collisions of two particles with one another. So when two particles collide, strike one another, they kind of ping off one another, bounce off one another. There's a momentary interaction between the two particles, and then they bounced off one another. When two waves collide, those two waves kind of coalesce with one another. And then they emerge from one another. And so the collision between particles, this sort of momentary collision between particles where they ping off one another, is very different from the collision between two waves, where they kind of slowly merge together and then slowly fall apart. And interference occurs in that collision of two waves, when they're overlapping with one another. So when we see interference, we see two kind of classifications of interference. One is called constructive interference. It's on this slide. The second one is called destructive interference. It's on the next slide. And in constructive interference, when the two waves are constructively interfering, you get bigger waves. And when there's destructive interference, when two waves destructively interfere, you get smaller waves. So I just want to show you how that works as waves collide, coalesce with one another. In this slide here, over here on the left-hand side, we're imagining two waves, wave number one upstairs, wave number two downstairs, colliding, coalescing with one another. So these two waves are superimposing themselves on each other. And together, they superimpose to make this wave over here on the right-hand side, which is the superimposed wave, which, as you can see, has a larger amplitude, a larger size than the two individual waves. That's occurring because this is an example of constructive interference, where when wave number one is a crest, so that's upstairs here, wave number 2 is also a crest downstairs here. When wave number 1 is a trough, then wave number 2 is a trough, and so on and so forth. Here's a crest, and here at the same time is a crest. Here's a trough, and here at the same moment is a trough. So when the two crests occur at the same time, you get a bigger crest. When the two troughs occur at the same time, you get a bigger trough, and so on and so forth. A big crest here, a big trough here. That's constructive interference. This is destructive interference, kind of the opposite. Again, over here on the left, I'm picturing two waves. Wave number 1 upstairs, wave number 2 downstairs, and I'm imagining these two waves colliding or coalescing or superimposing with one another to make some resulting wave from that collision, that superposition. And in this case, right, these two waves collide with one another and they superimpose actually to cancel each other out. So what's happening here? When wave number 1 is a crest, that's this moment here, wave number 2 is a trough, that's this moment here. And so the crest and the trough cancel each other out. When wave number 1 is a trough, wave number 2 is a crest. So again, a crest and a trough cancel each other out. This also happens here. You've got crest, you've got trough at the same moment. Cancellation. This happens here. You've got trough and crest at the same moment. Again, cancellation, and you get this destructive interference where the two combined waves, the superimposed wave looks like the waves have vanished. So that's destructive interference. Those are obviously two extremes of a whole world of interference, right? We picture constructive interference when crest and crest are exactly the same moment. Destructive interference where trough and crest are exactly the same moment. So those are two real extremes of interference. When we talk about interference of waves, constructive interference, destructive interference, we use a couple of terms. We're going to use a term which is phase, and we're going to use a term which is coherence. So I wanted to explain what we mean by phase and coherence. On this slide, I've just reproduced on the left-hand side the constructive interference from 2 slides ago of 2 waves, 1 and 2, and the destructive interference of 2 waves from the previous slide. So the constructive case, we made a bigger wave. The destructive case, we canceled out the waves. So what is phase? What does the word phase mean? Phase means where you are on the cycle of the wave, the moment you are on the cycle of the wave. So it means the crest or the trough, or in here, halfway between, is the node. It's a way of referencing where on the cycle. Where on the cycle, meaning, are you at the crest? Are you at the trough? Are you at a node? Or are you somewhere else on the cycle? So that's what we mean by phase. Where on the cycle? Coherence means that when you've got 2 waves, if they're coherent, if I say those 2 waves are coherent, that means that there's always a fixed phase difference between the 2 waves. So that no matter where we look at the 2 waves, in a sketch of the 2 waves, we always see the same phase difference between the 2 waves. There's always the same difference between the cycles of the 2 waves. So if you look at this case up here, where we had constructive interference, these 2 waves are coherent because there's always a fixed phase difference between the 2 waves. And actually, in this case, we would call that phase difference 0 degrees. You see, when this is a crest, wave 2 is a crest. When wave 1 is a trough, wave 2 is a trough, and so on and so forth. There's 0 degrees of phase difference between these two. So they are coherent, and their phase difference is 0 degrees. That's when you get constructive interference. Going downstairs here to the lower example of destructive interference, in this case, right, these 2 waves are again coherent. there's a fixed phase difference between the wave number 1 and wave number 2. But it's not 0 degrees. If you look, wave number 1, when it's a crest, wave number 2 is a trough. That's a half a cycle away. That's 180 degrees of a cycle of 360 degrees away. So here there's a 180 degrees phase difference. And that phase difference persists, right? Here the wave number 1 is a trough, wave number 2 is a crest. Again, that's half a cycle difference between the two waves. So half a cycle difference is half a complete cycle of 360 degrees, which is 180 degrees. So there's 180 degrees phase difference here. And again, there's 180 degrees phase difference at this point, right? This is a crest, this is a trough. They're separated by half a cycle, 180 degrees. So in these two cases where we see interference, it's either constructive or destructive interference, I would say that this is because these waves are coherent. There's always a fixed phase difference between them. And in one case, the constructive case, the phase difference is 0 degrees. In the other case, the destructive interference, the phase difference is 180 degrees. And so that's that language of coherence of waves and of phases and phase differences of waves. When we see interference, the waves have got to be coherent. When you see constructive interference, there's a certain phase difference. When you see destructive interference, there's a certain phase difference between the waves. This slide is the key to what's going to happen, what's going to go on when we look at the two-slit experiment. We're going to be observing coherent waves interfering with different phase differences. And when we look at the soap bubbles, we're going to see waves interfering with coherent waves interfering with different phase differences to explain the soap bubbles. Okay, here's just a little picture of wave interference. This is water waves, not light waves. And it's easy to see wave interference with water waves. It's much harder to see wave interference with light waves. The reason for that is that, water waves have wavelengths that are some centimeters, or maybe in the ocean some meters, and centimeters and meter ocean waves or water waves are very easy for us to see. And so it's very easy for us to see the interference of water waves, of those types of wavelengths. Light waves, much shorter. So it's going to be harder to see the interference of light waves. So if you look on this sketch here, not a sketch, it's a picture, there's a source of water waves over here on the left, at this location here. And so somehow, I don't know how, we're making water waves at that location. And those water waves are these circles of crests and troughs that are emerging out from that source of water waves. And then over here on the right-hand side, we're also making some water waves. Again, I don't know how, but again, there's a source of water waves, and those circles, those concentric circles of water waves, of crests and troughs and water waves, are merging outwards. You can see them as bright and dark fringes or lines on this photograph. Look down here. This is a really interesting region. This is a region some distance from the source on the left, some distance from the source on the right, where the two waves are interfering with one another. They're colliding, they're coalescing, they're merging, and we see the interference of the waves. We see crests and troughs interfering to produce destructive and constructive interference. So in this region here, you see bright and dark patterns. And the bright and dark patterns correspond to regions of constructive and destructive interference. They correspond to regions where the two waves either have phase differences that are small, 0 degrees, so you get constructive interference, or phase differences that are near half a cycle, 180 degrees, so you get destructive interference. So we're seeing that a pattern of constructive, destructive interference in here. And our task is really to see this with light. So go back a couple of hundred years, scientists were focused on trying to detect such patterns in light. So I want to make the point, stress the point, that that's going to be tough, right? Water waves add wavelengths of centimeters to meters. We can easily see centimeters to meters. Light waves have wavelengths that, if you remember, are 400 nanometers to 700 nanometers. So that's the range of visible light. So 400 to 700 nanometers, those wavelengths are less than 1 micron, which is less than a thousandth of a millimeter. There's no way, even with your eyesight, that you're going to see a wavelength that is shorter than a micron. That's not possible to see that directly. It's not possible to directly observe the interference, the wavelengths of light. So we need to be ingenious. The two-slit experiment is ingenious to see the interference of light, wave properties of light. Or we need to be lucky with natural phenomena to see the interference of light and the wave properties of light, and that's the soap bubbles. So we're going to look at those two examples, illustrations. Okay, so this is quite a busy slide, but I've got a few more slides that will kind of explain the details of it. But this is the famous Young's two-slit experiment. This was done in the 1800s. And this demonstrated that light clearly exhibits in a tabletop experiment wave properties. So it, at the time, it's now still considered, right, a landmark experiment, a brilliant experiment. So let me tell you about two-slit experiment. So over here on the left is a source of light. And this source of light, we're going to imagine that it's a source of a single wavelength of light, or a single frequency of light. So that's what monochromatic means. It's a single wavelength or frequency of light. That's the way to think about this experiment. That light is shone onto this arrangement here, which is basically going to impede the light, right? The light can't get through this arrangement here except through two very narrow slits. So S1 is a narrow slit upstairs here, and S2 is a narrow slit downstairs here. What Young was doing was taking that monochromatic light source and making two very small sources of light from that. So light is going to emerge through this slit upstairs here, and light is going to emerge through this slit downstairs here. So he's made two sources of, think about it, this is coherent light. It's come from the same source, got the same wavelengths, got the same frequencies, and so we've got two sources of coherent light. He's made an arrangement with which to explore that destructive interference that we sketched out earlier on and that we looked at with water waves. These slits have to be very, very narrow, and these slits actually have to be very, very close to see this effect. So it wasn't trivial to just, poke a couple of holes in a bit of cardboard or something like that. It was quite a bit of engineering at the time to make two very narrow slits very close together, because the scale here has to be, very small because the wavelengths of light are very small. Okay, so out of these slits come the light, And what you're seeing in this sketch, right, it's a little hard to see, but there are dark brown semicircles, and there are light brown semicircles. Here's me trying to indicate the light brown ones, and here's me trying to indicate the dark brown ones. The light brown ones are centered on one slit, and the dark brown ones are centered on the other slit. So the dark brown are emerging from the lower slit, the light brown from the upper slit, and they represent the crests of the waves, of the light waves that are emerging from the top and the bottom slits. So it's just a sketch of, look, I'm hypothesizing I've got light waves coming out of the bottom and the top slit, and those light waves have a certain wavelength, they have crests and they troughs, and I'm just going to draw all the crests. And so I've got this pattern of crests that flows across this region here out of the top slit and flows across this region out of the bottom slit, and those are going to interfere. And when you get crest and crest, as we now know, we're going to get constructive interference because we've got phase difference 0 degrees. When we get crest and trough, we're going to get destructive interference because we got two waves that are half a cycle apart, 180 degrees phase difference. And so we're going to get regions of constructive interference, and we're going to get regions of destructive interference. And you see these red dots and these red lines? These are marking the regions of constructive interference. And the black dots and the black lines are marking the regions of destructive interference. So let's just walk along a red line. If we walk along this top red line, we see that whenever the wave from the bottom slit is a crest, the wave from the top slit is also a crest. It's true here, it's true here, it's true here, and so on and so forth. So everywhere along this line is constructive interference. Crest meets crest at every location. If we look at this black line, well, let's pick this point here. When the wave from the bottom slit is a crest, actually the wave from the top slit is a trough. We're halfway between crests. So this is destructive interference. That's true here too. When the wave from the top slit is a crest, the wave from the bottom slit is halfway between crests. It's a trough, so we get destructive interference here. So destructive interference is occurring along this black line. So everywhere along the red line, constructive interference. Everywhere along the black line, destructive interference. And if you were to check, every other red and black line has that arrangement. All the red lines correspond to a direction of constructive interference, and all the black lines correspond to a direction of destructive interference. So the key thing about the two-slit experiment, the two sources of light, is that they produce a pattern of interference, constructive, destructive interference, where in one direction you're going to get constructive interference, in another direction you're going to get destructive interference, and that keeps repeating. If you were to put a screen over here, so this is what is done in the two-slit experiment. If you put a screen far away from the slits, so this distance to the screen would be meters. This separation between the slits would be maybe fractions of a millimeter. So this is not to scale. But if we put a screen over here, what do we see? What you would see is a pattern, is shown here, of bright and dark bands. You get bright bands where you get constructive interference, and you get dark bands where you have destructive interference. And we actually label those bands with numbers, with integers. So right in the center of the pattern is a maximum. We call that the 0th order maximum. Its neighbors are minima. So these are dark fringes, dark bands. And we call those the 0th order minimum. Next to the 0th order minimum, just above it and just below it, you see this maximum here, the first one below the horizontal. This maximum here, the first one above the horizontal. Those are the first order maxima. And then beyond those, there's the first order minimum. And then beyond that, there's the second order maxima. This one right upstairs here, this one right downstairs here. There's this whole spectrum. There's this whole pattern of these dark fringes. It's really an amazing thing to see. And they reflect the interference of the light from the two slits. They're demonstrating that light has wave-like properties, and they actually reflect the wavelength of the light. We see how they kind of, their pattern contains the wavelength of light, is a signature of the wavelength of the light. So just to stress again, because that slide was so busy, so why not have another busy slide? You get bright fringes. Here's an example of a bright fringe. You get bright fringes when the 0th order bright fringe is when, for example, the path from the slit upstairs and the path from the slit downstairs is the same. And so that the number of complete cycles of the wave from the slit downstairs and the slit upstairs to the screen is the same. And so for the bright 0th order bright fringe, when a crest is at the screen from the top slit, a crest is at the screen from a bottom slit, and so on and so forth. So that's the 0th order bright fringe. What about an nth order bright fringe? So this middle picture here is the explanation of the nth order bright fringe. So here's light coming from the top slit down to this location. Here's light coming from the bottom slit to this location. Now the paths are different, right? It's further from the top slit. It's less far from the bottom slit. You get a bright fringe here if the extra path that's taken by this upper light compared to this lower light is a whole number of wavelengths. So the first order bright fringe is when this is one extra wavelength. Second order bright fringe when there's two extra wavelengths. Third order when this is three extra wavelengths, and so forth. So that's the nth order bright fringes. What about the dark fringes? So here's an example of a dark fringe in this picture on the right-hand side. Again, we got the two slits on the left, we got the screen on the right. There's clearly an extra distance that the light from the top slit has to go compared to the light from the bottom slit to reach this location on the screen. If this extra distance here is half a wavelength, or 3/2 of a wavelength, or 5/2 of a wavelength, or 7/2 of a wavelength, that means that on the screen you're going to get, when one's a crest, the other's a trough, and vice versa. So this is the recipe for destructive interference. The 0th order destructive interference is when this extra distance is half a wavelength. The first order is when this is 3/2 a wavelength. The second order is when this is 5/2 a wavelength. So that's an explanation in terms of the wavelengths, the extra distances, the extra paths and wavelengths. It's an explanation of why you get the constructive, destructive interference in the bright and the dark fringes. I want to show you a kind of an example of this, a demonstration of this. I got here, this is a ripple tank. So there's a little tank of water up here. And I've got a device that makes two sources of water waves in this ripple tank. One that's near you and one that's further away from you. And so I'm going to, when I switch that on, it's not on right now, it's going to make these two sources of water waves, and those water waves are going to stream from the right over towards the left. And it's like the two slits in the Young's two-slit experiment, except it's with water waves rather than with light waves. Those water waves will interfere with one another, and we'll see this interference pattern. And we'll be able to see regions of constructive, destructive interference. We'll be able to see regions and how that pattern depends on the wavelength of the water waves in this case. So I'm going to switch it on. Now, you can't look down at the water waves on top, so there's actually a mirror there's a 45-degree mirror beneath the ripple tank, and it's going to reflect the pattern onto this white screen here. So you'll be able to see it here. So I'll set the mood. Where's the switch? So what you're seeing now, here's a source of water waves. Here's a source of water waves. It's like the two slits, isn't it? It's exactly like the two slits. And you're getting patterns, you can see them, of crests and troughs that are emerging from the two slits across the screen towards the left-hand side. And you're seeing their constructive and destructive interference. So you're seeing regions, darker regions, lighter regions, which correspond to the constructive, the destructive interference of the water waves. You can see the wavelength of the water waves on here. It's the distance between consecutive bright rings that emerge from one slit or the other slit. So right now you're just seeing the pattern of waves. There's a stroboscopic light on this device. If I switch that on, it just flashes every time the wave from these two slits is a crest. What it does is, because it flashes in phase with the waves, in sync with the waves, it freezes the waves. So you can really see the pattern of interference of the waves coming from the bottom slit downstairs here, the top slit upstairs here. And so you see these little dots of black and white where you're getting constructive, destructive interference. I hope you can see, imagine these lines, these sort of lines radiating outwards, which are the regions of where you get the bright fringes and the dark fringes. So you could really imagine over here on the, if I go over here on the right-hand side, I think I can see a bright fringe here. And then there's, look, this gray. This is kind of destructive interference. So there's a dark fringe here. There's another bright fringe here, dark fringe here, and so on and so forth. And that's exactly what's happening in the two-slit experiment. If I was to change the wavelength, what have I done? Let's change the wavelength. Let's make the wavelength longer. So the distance between crests is longer now. And you see how the pattern stretches out, how the interference pattern depends on the wavelength. If I freeze it, you can see that more clearly. And you see that we've changed, I won't go into the details, we've changed the pattern of bright and dark fringes over on the right-hand side. Okay. We need an equation, of course. No physics experiment would be complete without an equation to describe it. We needed an equation to describe the locations of the bright and the dark fringes, say their positions on the screen, or their directions towards the screen, in terms of the parameters of the experiment. So the parameters of the two-slit experiment are the separation between the slits, they're the distance to the screen, and they're the wavelength of the light. So I'm not going to spend much time on this slide here. I really want to spend a bit more time on the equation on the next slide. But the point is that the light emerges from these two slits. If we're going upstairs here, the light coming from slit number 1 takes a little extra distance, has to travel a little extra distance. And that distance we can write in terms of the slit separation and the angle towards the screen. So that's theta here. So the extra distance is the slit separation times the sine of the angle. Or, given the fact that the screen is very far away and the two slits are very close, we can actually write it approximately as the slit separation times the position on the screen divided by the distance of the screen from the slits. So this is a second way of writing it. So this is the extra distance, d sine theta, or dy over L. This is the extra distance that the ray that has to go the greater distance has to travel. It's the extra distance. And we've said if that extra distance is a whole number of wavelengths, we're going to get constructive interference. If it's a half integral number of wavelengths, so 1/2, 3/2, 5/2, then we're going to get the destructive interference. So this is what determines constructive destructive interference, this extra distance. So I'm going to show you on the next slide the equation for bright fringes, that's upstairs here, and the equation for dark fringes on the screen. These equations show you the location of the bright fringes and the dark fringes in terms of the angle towards the screen, so the direction towards the screen, or they show, so that's the theta, or they show you it in terms of the position on the screen, from the center of the screen, measured from the center of the screen. That's the y. And they show you the location of the bright fringes and the dark fringes. It depends on the wavelength of the light, and it depends on the slit separation, and it depends on the distance between the slits and the screen. So that's the lambda, that's the y, and that's the L. So let me just talk about the bright fringes. You get bright fringes when that extra distance is a whole number of wavelengths. So m lambda here, m is just an integer. So if the distance for the two waves coming from the two slits is 0, then if that extra distance is 0, then you get the 0th order bright maximum. If it's one wavelength, you get the first order bright maximum. If it's two wavelengths, m equals 2, you get the second order bright maximum. So if d sine theta or dy over L is 0 lambdas, 1 lambdas, 2 lambdas, that's bright fringes. The dark fringes. You get the dark fringes if that extra distance is a whole number, half integral number of wavelengths. So if that extra distance is a half a wavelength, or 3/2 a wavelength, or 5/2 a wavelength, then you're going to get a bright fringe here. And so this equation expresses the dark fringe. This equation expresses the location of the dark fringes in terms of the direction theta or the position on the screen y. So if m equals 0 here, that means the extra distance is half a wavelength. You get the 0th order dark fringe. If m is 1, that means the extra distance is 3/2 a wavelength. You're going to get the first order dark fringe, and so on and so forth. So this is the slide that contains the master equations for the directions of the bright and dark fringes, or the locations on the screen of the bright and dark fringes. So this is the sort of the key equations describing the two-slit experiment. Let me just show you an example calculation with the two-slit experiment. So that's this example here. We got a two-slit experiment, and in this particular case, the separation between the two slits is 2.1 millimeters. So it's just a couple of millimeters. They're really, really close. The distance to the screen is 1.75 meters. So, that's greater than my wingspan. So you see there immediately, right, that when I was drawing the sketches of the two-slit experiments, it wasn't to scale. The slits are really, really close to one another, and the screen's a long way away in relation to that. We're told that when we shine light on the two-slit experiment, the distance between the first and second order bright fringes, so these would be the first one and the second one away from the central bright spot, is 0.5 millimeter, 0.55 of a millimeter. So again, that distance is tiny. And based on that information, we're going to figure out what the wavelength of the light is. So we can literally, we're not only seeing that light is a wave, has wave properties, but we're also able to measure the wavelength of the light based on the knowing the dimensions of the experiment and where the fringes are. So let's see if we can do that. Okay, so here I sketched out the problem. I listed the numbers we were told in the problem, the slit separation, but I wrote that down wrong. Gosh, that's dyslexia, 2 point. Okay, glad I caught that one. Slit separation 2.1 millimeters. Slit to screen is 1.75 millimeters. Distance between two neighboring bright fringes is 0.55 of a millimeter. Now, the master equation for all this, I wrote it down, we'll write it down again, is this guy here. So this is the equation that tells you where the bright fringes are located. It tells you where the bright fringes are located. That's the Y. That's where on the screen they're located. In terms of the wavelength of the light, the slit separation, and the distance to the screen. Now, we're actually not told the location of a bright fringe. We're told the difference between two bright fringes. So I'm going to use this in a slightly different way. What I'm going to do is I'm going to rearrange this a bit. Firstly, I'm told I put a label on the Y's here. This is the second order position, and this is the first order position for the bright fringes. We're told that. The second order one, based on this equation over here on the left, is when m is 2. So if I plug in m equals 2, and I write this equation for y2, I'm going to get a 2 lambda, and I'm going to have to multiply by L and divide by D. So that's taking the master equation and just rearranging it for y2. Let me do the same thing for y1. y1 is when m is 1. So lambda equals y times d divided by L. Now, if I rearrange it for y1, so that's, again, dividing by d and multiplying by L, I'm going to get a lambda L over d. And so what we've made for ourselves here is a little equation that says y2 minus y1 equals, well, we got 2 lambda L over d minus a lambda L over d. So this is just going to be a lambda L over d. And we want the wavelength. And if we just divide by L and multiply by d again, it makes me wonder why I did that in the first place. I'm going to get this little guy here, which maybe would have been obvious originally. If I plug in the numbers, so I've got to plug in 0.55 of a millimeter for the difference between the fringes on the screen. I've got to plug in the slit separation of 2.1 millimeters. I've got to plug in the distance L. I've got to plug them all in the same units, right? I could plug them all in millimeters and get an answer in millimeters, or I could plug them all in meters and get an answer in meters. The answer that I got after doing all this was 662 nanometers. And so that is the wavelength of light. We've measured the wavelength of light by the position of these fringes, and we found that it's 662 nanometers. If you remember, light is from 400 to 700 nanometers, visible light. So it's a relatively long wavelength light that we've found here. Okay. Oh, I got a quiz question. I didn't know that was coming up. So in this quiz question, it says we've got a two-slit experiment, and we're going to increase the wavelength of the light. So we're going to make the wavelength of the light longer. So the question is, does that increase the separation between the fringes? We just looked at the separation between the fringes. Or does it decrease the separation between the fringes? Or does it not change the separation between the fringes? So I'll give you a minute or two to think about that, and maybe think about the equations that describe the two-slit experiment, and what would happen if you change the wavelength to the position of the fringes. Okay, so if you increase the wavelength of light, then to get constructive interference, supposing to get the path to be one extra wavelength, you need a greater distance. You need a greater path length because the wavelength is longer. The length of the wave is longer. And so to get a greater path length, to get a greater extra path, you're going to have the location on the screen move away from the center of the screen. So as lambda goes up, the position of the fringes, the bright fringes and the dark fringes, all move away from the center of the screen. As lambda goes down, as you make it smaller, they would all move towards the center of the screen. And so that's what that equation for the two-slit experiment is describing, that if you adjust the wavelength, you will stretch out the pattern, or you will compress the pattern as you stretch out the wave, or you compress the wave. Okay. Well, she hasn't been to class for a while, so I was disappointed. I am a member of a fan club, and she hasn't been coming to class, but she came to class for this one because it's a really important point. This experiment was the moment we understood really what color is. Color is wavelength. So Young's experiment was able to show that red light had a certain wavelength. Young's experiment was able to show that green light had a certain characteristic wavelength. So it was Young's experiment that was the key to understanding the nature of color. And the nature of color had been a long-standing question. What was color? What did color mean for light? Well, it's a reflection of the wavelength of the light. Red light is a long wavelength light, about 700 nanometers. Violet light is the short wavelength light. It's about 400 nanometers. So it was a really important experiment in showing you the wave properties of light. It was a really important experiment in understanding the nature of color. And we actually have the experiment here. So I just want to show you the experiment. If I can. I've got two sources of light, a red light and a green light, and I'm shining them on a pair of slits, two slits that have a very, very small separation. It's a fraction of a millimeter. And then we're shining that pattern on a screen that's several meters away. And I hope you can see that this red light is a series of bright fringes and dark fringes. And this green light is also a series of bright fringes and dark fringes. Now, the green light is the shorter wavelength. So these fringes are closer for the green light, and these fringes are farther apart for the longer wavelength red light. And so this is literally the Young's two-slit experiment. We borrowed it from the museum, and here are two different colors of light in the experiment shone on the two slits, and you're seeing this fantastic pattern. So this is really, you are literally seeing this, the wave properties of light, which was, you know, a magnificent moment in physics. Okay. Yet again, the slide has fallen over to the left of the room. Let's try and do soap bubbles. I am actually panicking right now because all this time I've been thinking, you're not giving enough time for soap bubbles. You're not giving enough time for soap bubbles. I'm just thinking that over and over again, ruminating on it, and I can't focus on what I'm meant to be doing. Anyway, soap bubbles. Look at this beautiful pattern in this soap bubble. Look at all the colors you're seeing in the soap bubble. There's regions of violet, there's regions of red, there's regions of green. We know now that these are regions of violet light interference, red light constructive interference, green light constructive interference. This is a natural example of wave properties of light and the meaning of the color of light that simply occurs in nature. Like when I was a toddler, I was doing this all the time, blowing these bubbles, and I didn't realize, you know, the importance of my work. Okay, so let's see if we can explain this in terms of light. Here is a little section of a soap bubble. And so this little diagram here is going to explain this interference pattern. And then we're going to come up with an equation for this interference pattern. So when we're seeing the light, the rainbow colors in the soap bubble, what you're actually seeing is light that's reflected off the soap bubble, and it's actually reflected off two surfaces of the soap bubble. It's reflected off the outer surface of the soap bubble, and it's reflected off the inner surface of the soap bubble. So the soap bubble is a very, very, very thin film of soapy water. Obviously has air on the inside, air on the outside. It has this very thin thickness, and we're seeing light that's actually reflected off the outer surface and the inner surface. So that's a key point about this. This is what I'm drawing in this picture. So here's a light ray coming in towards the soap bubble. This is the outer wall of the soap bubble. Downstairs here, this is the inner wall of the soap bubble. And we see, as I said, light being reflected off the outer surface. I called that ray number 1. Light being reflected off the inner surface, I've called that ray number 2. So we've got, like the two-slit experiment, this is clever. like the two-slit experiment where we had two sources of same wavelength coherent light, now we've got in the soap bubble two sources, reflection off the top, reflection off the bottom, of coherent same wavelength light. And so, you know, the same effects that we saw in the two-slit experiment we're going to see in the soap bubble phenomena. We're going to see constructive and destructive interference of these rays number 1 and rays number 2 from the bottom and the top surfaces. And that constructive destructive interference is going to be determined by whether the extra path that's traveled by the ray that gets reflected off the bottom surface rather than the top surface corresponds to a whole number of wavelengths or corresponds to a half integral number of wavelengths. There is one little extra subtlety I've got to mention because it comes up in the equations. For that is a difference between what's happening here with the soap bubble and what's happening with the two-slit experiment. And it's the following phenomena, which was a mystery for a long time. It is now understood. I'm just telling you it's understood. I'm not going to explain how it happens. But when you reflect off a higher refractive index medium, so we got air, lower refractive index, water, higher refractive index. When we reflect off a higher refractive index medium, the phase of the wave actually changes by 180 degrees, half a cycle. So it goes, at the moment it reflects, it goes from crest to trough, or trough to crest. It does that when you reflect off a higher refractive index medium. When you reflect off a lower, when you reflect off a lower refractive index medium, in that case, you don't get the phase change. So downstairs here, there's no phase change. This is reflecting from higher refractive index medium off a lower refractive index medium. So there's no phase change here. So everything is kind of like the two-slit experiment with two sources of coherent waves interfering with one another and getting constructive, destructive interference, and that to be determined by the extra path, except there's this one subtlety that off the top surface you get a extra flip of the phase from crest to trough or trough to crest. You don't get that on the bottom surface, and so that has to be accounted for in the equations. Here is the two equations. So these are the equations that parallel the two equations for the two-slit experiment. We remember we have one for bright fringes, one for dark fringes. Here we got one for bright fringes and one for dark fringes on the soap bubble. When you've got bright fringes, that means that you've got crest and crest for the two reflected waves being coherent, 0 degrees phase difference between the coherent wave, the reflected waves. When you've got destructive interference, you've got a crest and a trough, or a trough and a crest. You've got 180-degree phase difference between the two reflected waves from the top and bottom surfaces. So these are the formulas. 2t. 2t is the extra distance that is traveled by the wave that comes off the bottom surface compared to the top surface. Now we imagine the wave is going straight 90 degrees to the surfaces. So the extra distance is simply the thickness of the film. It's simply twice the thickness of the film because you've got to go through the film once to reach the bottom surface and then back through the film to get out of the soap bubble. So the extra distance traveled by the wave reflected from the inner surface is twice the thickness of the soap bubble. And it's always that's always the extra distance. If that extra distance is a half integral number of wavelengths, you actually get a bright fringe. If that extra distance is a whole number of wavelengths, in this case you actually get a dark fringe. And that's because of that extra change from crest to trough or trough to crest from that reflection of the of the higher refractive index material, the top reflection, the one on the outer surface of the soap bubble. So this is counterintuitive if you think about the two-slit experiment, is because of this ingredient in the soap bubble that's not in the two-slit experiment, the phase change on reflection. Okay, so let's take a look at the bright fringes. So this says that if you've got this distance, extra distance, 2t, is a half integral number of wavelengths. So half a wavelength, 3 halves a wavelength, 5 halves a wavelength, 7 halves a wavelength. That's when you're going to get a bright fringe. That's when you're going to get constructive interference. Now we have to be a bit careful. Look, I've written lambda n. This is the length of a wavelength in the soap bubble. Now the soap bubbles, the wavelength got shrunk in the soap bubble by a factor of the refractive index. If you remember from our discussion of refraction, when you enter into a higher refractive index material, the wavelength actually shrinks, like the speed actually shrinks, and both of them shrink by a factor of the refractive index. So this extra distance in the soap bubble has to be a half integral of number of wavelengths in the soap bubble. So I wrote that as lambda n. Or you can alternatively write that as the wavelength of the light in empty space divided by the refractive index. So lambda n and lambda over n are the same wavelengths. They're just a different notation. Either I can say it's the wavelength in the water, or I can say it's the wavelength in empty space divided by the refractive index of the water. Then downstairs, here's the second equation. This is for the dark fringes now. You get dark fringes when this extra distance, 2t, down through the soap bubble and back up to the top of the soap bubble, equals a whole number of wavelengths. Again, that's counterintuitive. It's counterintuitive because you had that extra flip of the phase when you reflected off the top surface, but not off the bottom surface. So if this extra distance is 1 wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths, you're going to get destructive interference. You won't see any reflected light at all. Now, again, important point, if that extra distance is 1, 2, 3, 4 wavelengths of the light in that material, in that medium, in the water of the soap bubble. So that's why I wrote it as lambda n. This is the wavelength in the soap bubble, which we could alternatively write as the wavelength in empty space lambda divided by the refractive index of the material of the soap bubble, the water of the soap bubble. So this equation and this equation are the same equations, but really just a different way of expressing or writing the wavelength of the light in the water of the soap bubble. And so these are the two equations that we use for soap bubbles. Show demo of soap bubble interference. Yeah. Good luck. So I could try this, but it's not going to work very well. So I've got a little soap bubble in here. And if I wiggle it around, maybe a few of you might catch a glimpse of colors. I don't know. You may or may not. But I made a little movie of it. So I want to show you the movie. You can come and play with this later on. I think any demonstration with water is fantastic. I love all the water demonstrations, and so this is a good class for me. What was I doing? I was going to show a movie. Okay, so in this movie, it's just made with this soap water and this little ring here. I made myself a soap bubble, and we made a movie of it. And look, you see this pattern of colors. This is a pattern of colors caused by constructive destructive interference of light from a lamp reflected off that soap bubble. And so you see certain regions where that extra distance is just right to make the constructive interference of green light, of red light, and other colors of light. And you see this pattern repeating because the thickness of the soap bubble is changing from the top to the bottom. It's thinner at the top, right? All the soap's running down. It's getting thicker at the bottom. And so it's not just a sheet of constant thickness. It's kind of like this, getting thicker and thicker as it runs downwards. And so you see these repeating rainbow patterns. And so let me just show you that. And those little patterns are literally, you're seeing the wave properties of light, the meaning of color of light, and so on and so forth. This is 22 seconds that took, if I remember, like 2.2 hours to actually get the camera to see it. But it was worth it in the end. I feel like I'm Steven Spielberg with that one. Okay, not really. Okay, I want to do a little calculation involving soap bubble interference. So in this particular case, in this particular question, we're told we got a soap bubble. The refractive index is the refractive index of the water, because it's just soapy water, so it's 1.33. We're told that this soap bubble has a wall thickness that's 120 nanometers. And that's, soap bubbles are extremely thin. That's why they exhibit this pattern. You also see it with oil on a roadway. You can see this pattern of different colors reflected and the interference from the bottom and the top surfaces of the oil on the roadway, again, because that's very, very thin. So we've got based on the refractive index of the soapy water and the thickness of the soap bubble, we've got to calculate the wavelength that is most strongly reflected. So let's see if we can do that. We've got a certain thickness soap bubble, think of that. We've got a certain refractive index for the soapy water, think of that. So there'll be a certain wavelength of light that the interference between the light that's reflected off the top surface and the one that goes the extra distance through the soap bubble down to the bottom surface and then back up again, when it comes out, it has 0 degrees phase difference. It interferes constructively. So let's see if we can do this. Now, they didn't tell us what order the bright fringe is, the bright light constructive interference is. So I don't know what order it is. And so the only thing I know to do in that situation is to start with the lowest order, so that's m equals 0. Try that and see if there's a visible light, if the wavelength that corresponds to that is visible light. If it is, you've found the wavelength, a visible light that's strongly reflected. If not, you're going to have to try m equals 1. And see if m equals 1, when you calculate the wavelength, you get constructive interference of visible light, and so on and so forth. So there is a bit of trial and error in the way this problem is set up, because we don't know, we weren't told m. If you remember the two-slit calculation, we were told m equals 1 and m equals 2. In this one, we're not told an m value. Okay, so I sketched out the problem here. Here's the incoming ray, and then we got the two reflected rays from the top surface, bottom surface. We're imagining a bright color being reflected, so constructive interference. We know the refractive index is 1.33. We know the thickness is 120 nanometers. We want to know the wavelength. Okay, so I'm going to guess m equals 0. And the master equation, right, if I write it down, is that for bright fringes is this one. So over here on the right is that extra distance that we travel, twice the thickness of the film. We've got a lambda over n. So lambda here is the wavelength in empty space. That's what I'm going to calculate. And n is the refractive index of the material, the water. And that's the amount that the wavelength shrinks in the water. And then the n plus 1/2, this is just our notation for 1/2 or 3/2 or 5/2 or 7/2. And as I say, I'm going to try m equals 0 and see if I use m equals 0, see if I get a wavelength that's a visible light wavelength. Okay, so I'm going to rearrange this for the wavelength with m equals 0. And so to do that, I've got to, let's see, this is very, simple algebra becomes extremely hard when you stand up here for some reason. But I think if I do it, I'm going to get 4n times t. So I've multiplied both sides by n. I've multiplied both sides by 2. Oh, that looks simple. All I've got to do to figure out the wavelength is plug in the refractive index, 1.33, and plug in the thickness of 120 nanometers. And if I multiply 4 times 1.33 times 120, I got 640 nanometers. So 640 nanometers is in that window of visible light. It is between 400 and 700. It's at the long wavelength end, so this is red light. And so what we're seeing here is a patch of bright red light on our soap bubble. That's the light that's being reflected and intensely. That's the light that's producing constructive interference. Anyway, I'm going to end there. We've spent the whole class on interference. What is interference? That was one thing we did. And we introduced some terminology of phase, phase difference, coherence, coherent waves. We then talked about the two-slit experiment. Fantastic experiment. Told us that light has wave-like properties, told us what color is. We looked at equations for the bright and dark fringes. We then looked at soap bubbles, also a fantastic phenomenon. Tells us that light is waves.